Students, we'll now like to understand more about dielectrics. So what exactly are dielectrics? Dielectrics are basically insulators, and insulators can also be classified further into some which are polar dielectrics and which are non-polar dielectrics. We'll try to understand more about this and how do these kinds of polarization of dielectrics helps us in storing amounts of charges, different amounts of charges. So these are the things that we are going to discuss in this particular part. So when we talk about the electrostatics of conductors, within a particular conductor, the electrostatic field, please understand it's not the electric field, we are talking about the electrostatic field here, that is going to be 0 because it's an equipotential surface. On the surface of a charged conductor, the electrostatic field must be normal to the surface. For instance, if I say that this is my conductor, then the electrostatic field has to be always like this, okay, and the potential is going to be tangential. So the electrostatic field has to be normal to the surface at every particular point. Further, the interior of a conductor can have no excess charge in the static situation. Whatever charge is there, if it's a conductor, that particular charge is going to be uniformly distributed throughout the conductor. So in the static case, there cannot be any amount of excess charge that can be present in the interior portion of the conductor. Going further, when we talk about the electrostatic potential is constant. It is a constant that exists throughout the volume of the conductor and has the same value as inside on its surface, because since it is constant, the complete charge is completely distributed uniformly, and therefore what happens is that it is going to be having the same value. The electrostatic potential is going to be same throughout, inside or outside the surface of the conductor. Going further, the electric field at the surface of a charged conductor, the electric field is always going to be on the surface of the charged conductor, because inside it is an equipotential surface, so there is not going to be any electric field. So if there is no electric field, that means the charge is not going to be experiencing any electric force. That is the reason there is no electric field inside it, there is only electric field outside it. Going further, there is something known as an electrostatic shielding. You would have heard in atomic theory or structure of atom in chemistry that when you have a considerable large amount of electrons, means if it's a big atom having a 3D shell which is filled, in that case the electrons in the 4s shell do face a kind of shielding from the inner electrons. So it's much easier to remove those electrons from the outermost shell. That is what is known as the electrostatic shielding that we have. Moving on, when we talk about dielectrics, so dielectrics is basically a materials which do not allow the current to flow through them. They are, you can say, not really conductors, but they can store charges. So these are materials which do not allow, this is very, very important. They can store charges, they can get ionized, but they will not allow the charges to flow through them. These are known as insulators or dielectrics, but you do use these dielectrics for certain reasons, to store charges, to increase the capacity and so on. That will come to in a slightly later on. In this case, the electrons in such materials remain bound within their individual molecules. So for instance, if you have this kind of a dielectric, obviously the total number of positive charges is going to be total number of negative charges because it is neutral. Further, why do we classify them as dielectric? Because the charges are not free. The charges are not free and therefore they are bound. Means they are bound in chemical bonds. They are not ionically bound, they are covalently bound, right? So that is the reason why we classify them as dielectrics, which are covalently bonded compounds. Going further, that they are affected by external electric fields. So when you do apply an external electric field, what is going to happen? So let's say you place them in front of charge place. For instance, this is plus charge, this is negative charges. So here you will get a positively charged region, and in this part you will have an equally charged negatively placed. So it is going to be equally distributed, right, such that the total neutrality is balanced. They do transmit electrical effects, which we are going to see when we discuss about the capacitance. Then you also have non-polar dielectrics. What exactly are non-polar dielectrics? In such dielectric, the center of mass of all the positive charges in a molecule coincides with the center of the negative charge. If you remember, when we discussed about, for instance, a dipole, if you take the case of HCl, even though HCl is a covalently bonded compound, so we should expect that the center of positive and negative charges is actually going to be at the center of the molecule, but that doesn't really exist. Instead, you have the structure of the molecule something like this, wherein this is the H part, this is the Cl part. Why do you have the bulging part over here in Cl? The reason being Cl captures the electrons. It basically takes the electron partially towards itself, and therefore it acquires a partial negative charge and hydrogen acquires a partial positive charge. So you have H and Cl. So this results, even though it is electrically neutral, but what you have in this, you have the positive charges coinciding at the positive charge center is different than the negative charge center, is not really at the center of the whole molecule, right? So this is what is a dipole. But if we talk about a neutral molecule, or basically a non-polar dielectric, in that case it's going to be completely at the center. So therefore then these molecules are not only electrically neutral but also possess zero dipole moment. Zero dipole moment because the center of positive and negative charges are exactly at the same point. Further, if you classify the polar dielectrics are those, as we understood for the case of non-polar dielectrics. In the case of non-polar dielectrics, what they had is this, that you had to have the center of positive and negative charges being exactly at the same position. But in this case, it is not the case. In the case of polar dielectrics, the center of the mass of the protons in a molecule does not coincide with the center of mass of the electron. That is, the center of positive charge is not at the center of the negative charge. This is the reason being, this is due to the asymmetric shape of the molecule, as I just mentioned in the case of HCl. So H2O is basically a neutral molecule, but in the presence of some dipoles, it does get polarized, right? So it does become a polar dielectric in the presence of some other dipole, but not in the absence of any other dipole, it is going to be a non-polar dielectric. So what exactly is polarization? Polarization basically means when the atoms of a dielectric under the action of an applied electric field move, and therefore the center of the positive and the negative charges are not at the center of the atom. That is what is meant by polarization. What exactly is polarization density? As the name itself suggests, if a molecule has got polarized, then how much has been the polarization? Obviously, the polarization is going to be uniform. So the dipole moment developed per unit volume of a dipole when you place it in an electric field, that is what is known as the polarization density. Then what we are going to discuss in the case of dielectric constant. Now let me just explain that. For instance, if you remember, I just said that if I have this dielectric, let's assume that it's a polar dielectric, and if I say that this part is positive, this is, you have a positive charge, here you have a negative charge, and so an opposite charge is going to be induced on this part, and similarly an opposite charge is going to be induced on this part, right? Further, we know that an external electric field is being acting, which is going to be acting like this. So if I say, so this is the external value of the electric field that is acting. Let's say E0 is the external value of electric field. Further, within the dielectric, as you can see, the induced electric field is in the opposite direction. Obviously, that's not going to be equal to the applied electric field. So if I say this is the polarized electric field, so what exactly is the net electric field? The net electric field is going to be E0, that is the applied one, minus the polarized one. So the net electric field is going to be given by this. Now let's try to understand what we have here. Suppose the dielectric slab is placed in a uniform electric field E0. The electric field will polarize the slab as the positive charges will be shifted slightly towards the right, as we have seen, and the negative charges will be shifted towards the left. The right surface of the slab gets positively charged, the left surface gets negatively charged, as we have seen here. So that tells us about this as being the net value of the electric field. But how much is the strength of this field? How much is the polarization that is produced? So that is given by the dielectric constant. So this is the applied electric field and this is the final result, right? Because this is how it is defined. So this particular ratio is known as the dielectric constant of the particular material. Finally, what exactly is the dielectric strength? So dielectric strength is basically as to of a dielectric is the maximum value of the dielectric field that can be applied to the dielectric without its electric breakdown. That is, without it breaking down into single electrons and protons. So it still remains its entity. Its entity it remains same. It is just that how much is the amount of electric field it can be induced in. That is what is meant by the dielectric strength. Hopefully you understood till this point. We'll go further and try to discuss more about it. Stay tuned.
So students, we learnt about what exactly is a conductor. When you have a conductor, like you would have understood in chemical bonding and chemistry, you know that the conductors have something like a metallic bonding. In that, any electron continues to be a non-part of that particular ion core. So you have the ion cores moving separately and the electrons moving separately. So this phenomena does exist in the case of conductor. That's the reason they conduct. But when we talk about non-conductors, which are also known as dielectrics, so in the case of dielectrics, they are nothing but insulators. We classified insulators into polar insulators and non-polar insulators. In the case of polar insulators, which are our main concern, in that you have the center of positive and the center of negative charge not placed at a single point. Therefore, these are the things, or these are the materials which help us in storing charges. Then, when you have these kind of non-polar conductors or non-polar dielectrics, I mean to say, these are further classified as to how much is the dielectric strength of them. Based on their dielectric strength, we can further classify them. So dielectric strength tells us as to how much is the amount of polarization that takes place when you place these dielectrics in the presence of an external electric field. So that is what is known as the dielectric polarization. So stay tuned now to understand about the most important thing, that is the capacitance.